Hello, welcome everyone. I would like to introduce Laurent and Daniel of Arion Group Nano Avionics. The floor is yours.
Okay, thank you, Jay. Hi, everyone. My name is Enguerrand Petit-Fils. I'm working for Nano Avionics UK, a satellite mission integrator. My colleague here, Laurent Cadet, is a civil engineer for Arion Group, a French manufacturer specialized in orbital launch vehicles, Ariane. His job consists in designing complex and sectorized buildings. We would like to thank the Mars Society, who gave us the opportunity to express our viewpoint on how civil engineering group projects could be led in order to build on Mars. In that way, we plan to give you a short overview of project management adapted for the construction of facilities on Mars. We're going to talk about standard input data, loads, materials, and risks. And then we will try to find some relevant information for civil engineers in the data collected for many years by the space agency's probes and sensors on and around the planet Mars. So in order to start your building project, you have to answer a few questions. So the first question is what? What do you want to build? Why are you doing this construction? And which project will need to be hosted? In which conditions will it be operated? What do you need? Do you need living quarters? Do you need laboratories? Do you need manufacturing halls? Do you need to do metal forming? Do you need to do farming? So on and so forth. You need also to know if you need to regulate the environmental conditions like temperatures, humidity. Do you need to filter the air? Do you need confinement? You need to understand exactly how you want to organize your rooms. Do you want to have a storage room next to the kitchen? Do you want to have a minimum distance between the launch pad and dormitories? And you need also to think about how to improve everyday logistics. The second question to ask is when? When do you want to start the design process? And when do you want to start, or when do you need to start digging? When do you need to start qualification testing? And finally, when do you need to build? You need the building to be fully operational. And related to that, you also need to answer the question of how long this project is for. What is the lifetime of this facility? The third question is, of course, how much? So if you've got infinite money, you can do everything but break the laws of physics. However, you are constrained with three factors: quality, time, and cost. And reality tells you that you can only choose two of those. One if you're tricky. Fourth question is where? Where do you want to locate your building? The Earth is quite diverse. Mars maybe a bit less, but it's still quite it still displays many different environments. So do you want to build in the polar regions? Do you want to build in the mountains? Do you want to build in the plains? Or do you want to build half underground in deep canyons? And how far do you want to be from the extracting site for the materials? And the fifth question to ask is how? How do you want to do it? So we talked about materials. Do you want to use materials on site, or do you want to bring materials from Earth? Do you want to have a hybrid approach? And who would be working for that? Do you need to have humans to work on it? Do you need robots? Do you need humans controlling robots remotely? And on your humans and robots, what skills do they need to have? Do you need to do drilling? Do you need masonry? Do you need iron workers, welders, and so on? On Earth, there are several design codes to cover the different aspects of civil engineering. The codes vary by locations. You've got one for different regions, and they also depend on the kind of materials. So on the project. So for instance, for buildings, you've got in Europe a code for conventional buildings, but you've got specific code for nuclear facilities. You've got different codes also for harbors and other specialized facilities. The code depends also on the materials. So you've got one code for concrete, one code for steel, one code for timber, for aluminum, and so on. And obviously, all these codes have been drawn during many, many decades, even centuries, on Earth, depending on the Earth's living conditions. They provide resistance to normal conditions and accidental conditions the way we experience them on Earth. And this may be different on Mars. So in the long term, there will need to be merchant standards. And obviously they will be inspired by Earth standards initially, but they will need to diverge at some point. You have to keep in mind that a structure is an amount of materials arranged in and organized to withstand loads and to transfer them to the ground thanks to a system of foundations. So for safety reasons, we had margins on materials. And safety coefficients are used to consider lower resistance for the materials, because any code, however good it is, cannot perfectly match the real phenomenon and possibly weaker materials. For instance, on Earth, steel and aluminum are manufactured materials with a production process that is well controlled, well managed. Concrete comes from aggregates, and cement have been extracted from the ground for many centuries, if not millennia. That's why additional margins on these structural materials are usually very low on Earth. But however, do we want to use such low margin on Mars? It's unlikely that we would bring steel, aggregates, sand, and cement from Earth. It would be difficult. So if they are manufactured and extracted from Mars, will we be able to reach the same quality standard in the manufacturing? So it seems easier it seems fair to consider that margins will be much higher on Mars to take into account the local difficulties. For metallic parts, it could be interesting to design dual structural elements. Beams and columns composing the first logistical vessels sent from the Earth could be recycled for civil work on Mars. Infrastructures are stressed by different kinds of loads. First of all, you've got permanent loads, which are also called dead loads. These loads come directly from the self-weight of the structural elements. And self-weight is directly linked to local gravity. So it will be, as the gravity is less strong on Mars, permanent loads will induce smaller structural elements. You also have additional permanent loads, which are not the building itself, but they are used to take into account the weight of the equipment that could be considered as stationary regarding the service life of the building. So they would be in the same category as the permanent loads. Another kind of load are the service loads. They come from the equipment, operator, and supplies needed to operate the life. They are much more dynamic, much more diverse. And while we can guess that they will also be reduced compared to the Earth conditions due to the lower gravity, they do not solely depend on gravity. So they will vary much more. And finally, you've got temporary loads for constructions. So these loads are only used during the construction process and are linked to the methodology used to build the structures, to take into account heavy loads temporarily stored at different locations of the building, and also to take into account construction phases when the entire structure is not finished yet. So they should not be forgotten because some structural elements can be designed by construction process. Sorry. External conditions such as wind speed, temperatures, and water table are constantly changing on Earth, and to some extent are also changing on Mars. They change every day depending on weather and seasonal events, and they have to be taken into account into a separate kind of loads called variable loads. On Earth, these values greatly depend on the site location, and even though Mars is a bit less diverse, it's still the case that they will vary a lot as well. So it's not the same if we are building something in Arcadia Peninsula or in Valles Marineris, with different temperatures and different pressures, different environments. Also, nature can dramatically affect infrastructures. So evidences of cavities below the foundations, flooding, mass quake, and extreme atmospheric conditions are generally taken into account by civil engineers. So here's a global topographic map of Mars in order to identify some different regions. We try to highlight the regions where probe has already been sent. And even if Mars is smaller than Earth, there is a wide dispersion of the probes on Mars' surface. This is good to understand phenomenon at the global scale, but civil engineers require a coherent set of data from a specific location, and therefore the current set of data is not sufficient. So Laurent will continue the presentation.
Yes, thank you, Laurent. So now we have collected data on Mars thanks to the probes sent by space agencies. How can we use them for design of civil infrastructures? Just as the Earth, Mars is a telluric planet which owns a core, a mantle, and a crust. Because this celestial body is made of a rocky surface, we can consider similar building methods, which consist in gathering loads in structural elements and allows their transfer to the soil thanks to a system of foundations. A fundamental difference of the Martian crust is that it appears to be completely motionless, as a difference to the tectonic plates on our planet. And Mars gravity is about 38% of Earth's one. Gravity is a major parameter for civil engineering, especially when building on another planet. And Mars is we can say that Mars is a very comparable planet to the Earth in terms of seasonality, thanks to its distance to the sun and thanks to its tilt angle. Like Earth, Mars has two polar ice caps. Mars Express results reveals that both polar ice caps are up to 3.5 kilometers thick. Each polar ice cap has a core of water ice, which is covered by a layer of carbon dioxide ice. These elements could be useful resources on Mars for humans and for constructions. When digging or building subsurface structures, it is necessary to identify water table level, and nature of liquid aquifers at the vicinity of the construction. In the design, force induced by the presence of liquid water is added to pressure induced by geologic layers. Obviously, this parameter can't be averaged at the global scale of Mars, nor at the regional level. So, hydrogeological studies must be led on the construction site before digging, and we can say before designing. Similarly, it's necessary to quantify force line variation below the surface. On Earth, depth of the foundation is also ruled by this parameter. On Mars, during the warmer summer months, most of the carbon dioxide ice sublimates directly to vapor and leaving behind the harder water ice layer. Civil engineers will have to cope with this issue because structures can be dramatically damaged by the movement of their foundation. And what about geology? The Martian soil is made of minerals such as olivine, pyroxene, amphiboles, feldspar, carbonates, sulfates, silicate, phyllosilicates, phosphates, and iron oxides. We also see a variety of familiar landforms like wind-formed sand dunes. So Mars and Earth's geology can be considered as very similar. The picture on the right reveals a significant geological issue for civil engineering. Outcropping salty rocks have been observed. In some regions, dark streaks observation have been explained as quick evaporation of seeping water, leaving salty deposits. Building in this area could dramatically affect the parts of the construction in contact with Martian soil. The durability and robustness of metallic structures have to be carefully studied in case of salty deposits. Now, data about atmosphere. On Earth, Köppen-Geiger climate classification system set 5 main climate groups based on seasonal precipitation and on temperature patterns. Of course, a wide range of subclimates does not fit to the Martian context, as there is no precipitation patterns perfectly comparable to Earth. So only ice cap climate and cold desert climate, which are Buildable UK and EF on the map, would really fit to Mars. The atmosphere is very thin, and the atmospheric pressure at the surface of Mars is only about 1% of Earth's one. So, low pressures make easier the implementation of an air pressure hierarchy inside facilities containing toxic or radioactive substances, except in case of fast and huge atmospheric pressure variation outside the building that could occur with accidental wind conditions. Dealing with wind and other atmospheric parameters, a relevant data to take into account in construction projects is to properly orientate the building on site. InSight mission also gives us day-to-day weather reports as well as seasonal data. The following record shows that air temperature close to the surface can be very low with huge daily variations. This is an important input data for civil engineers. The average temperature on Mars is about -60 Celsius, that can reach +20 Celsius in equatorial region. Depending on the season and on the location, temperatures can vary between -284 Fahrenheit and +86 Fahrenheit. These variations induced additional stress in the structure, especially for metallic structures. What about seismicity and volcanism? We have already talked about the fact that the crust seems to be motionless, whereas we have tectonic plates moving on Earth. And on Earth, tectonic plates plays a great role on Earth's volcanology and seismicity. As a regard to the data, seismic risk will not have a significant impact on Martian civil constructions. Volcanism seems to be a very limited tool and will likely not play a significant role. We are used not to consider volcanism risks on Earth, even for critical infrastructures. So it will be the same on Mars. But the issue about that is the dispersion of different type of rocks in the same area induced by volcanic ancient activity. It deserves to be taken into account as same as in the vicinity of meteorite impacts zone, because they can locally change geology at the surface. Then we have tornadoes and dust devils. On Earth, the impact of tornadoes is assessed during designing process for some critical infrastructures, such as nuclear power plants. Several tornadoes categories are used depending on the importance of the activity hosted in the facility. The impact of objects or vehicles projected by tornadoes on external structure is calculated, as well as the overpressure field induced by extreme windy conditions. On Mars, this risk should be taken into account as comparable atmospheric events have been observed. Obviously, wind pressure field will be adjusted to Martian environmental conditions. In addition, I've previously told that the atmosphere is light. It's light but abrasive, and the abrasive nature of sand projected by the wind would also be taken into account for lightweight constructions and for infrastructural elements exposed to external climatic conditions, such as doors, windows, air ducts, outdoor electrical equipments. A review of industrial risk at the vicinity of the building is mandatory in order to identify and to quantify industrial accidental loads. High-risk industries are used to consider post-explosion overpressure field, external fires, internal fires, load drops, air crashes, pressurized equipment explosion. On Mars, we believe that rocket launch and landing activity will generate at least two other risks. For example, an accidental impact with a lander or a rocket blast during a liftoff sequence could affect infrastructures. So, this presentation aimed to introduce the challenges for a civil construction project on Mars, following a realistic approach based on the long human experience on Earth. The way to perform such a process with Earth standards have been briefly presented in the first part. It appears that some input data have to be defined in order to properly solve critical issues, such as the choice in the type of structure, logistic for construction materials, robustness of structural elements, cost, and deadlines. In the second part, some data collected by Space Agency probes have given us precious information on environmental conditions that will stress Martian buildings. Using this data, we also try to reveal what is at stake for civil engineering design. For now, the regional dispersion of the collected data on Mars allows to identify a construction site, considering phenomenon at the global scale and considering risk at a regional scale. But there are not enough detail in order to focus on one possible construction site without starting the design with significant assumptions and huge margins. To conclude, Mars definitively seems to be a buildable planet, but the challenges are still significant. Designing process could start in few years with more data, or it could start now with huge margins, especially because accidents on Mars would have a much bigger impact. Then we can continue with iterative process to improve and to optimize the design. Civil engineers are now ready to make it possible. Thank you for your attention. If you have questions.
Okay, question from Orion. Can you discuss the design changes needed for pressurized buildings? Would 100 kPa internal pressure means the walls are holding the roof down, not up?
Can you repeat the question, please? Excuse me.
Yeah, it's in chat. I was wondering if 100 kPa internal pressure would mean the walls have the walls will be holding the roof down.
Environ.
Yeah. So that's actually something that, well, sort of changes. It's on one hand, the pressure will help you lift sustain the structure. So you don't have to worry too much about the structure if you are able to assume that you have a full pressure all the time. So it may not be doable. And yeah, instead of on Earth, it's quite easy to make a building that is fully it's using a load all the time. While because of these pressurized buildings, you will need to design so that you sustain loads, and you need to sustain shear and stress and stretch as well.
Yes, and it depends. It also depends on the type of construction. If you have metallic and lightweight construction with skin, it would be very different than concrete infrastructure, because in case of metallic structure and a skin, pressure variation is very important. The difference between the inside and the outside is very important. But for concrete structures, the overpressure mainly allowed to, say, expulse, to give up, chemical or radioactive bad substances outside.
Question from Sybil. Following your conclusions, do you think that the first humans to land on Mars should live above ground or underground?
It's a very interesting question. I think living underground is very interesting, but you have challenges you have issues to take into account. I told about, and Laurent told about water table, and the pressure of water, which is added to pressure of the soil. But living on the behind the ground or inside the ground helps you protecting from meteorites, protecting from the wind. It's very interesting, I think.
Yeah, you also have a middle ground, which is having surface structures that are buried within some dirt. This helps you with the radiation issues as well.
Yeah.
Hi, it's about the official end of the session. I can leave the room open for further discussion for another 10 minutes or so. And of course, Elon Musk is going to be talking about now.
Okay, thank you.
Thank you very much.